So again, this chapter we are talking about deriving thermodynamic models to calculate different thermodynamic properties for pure compounds. And so we are using these thermodynamic models if we don't have like tables in the appendix, or if we don't have figures that we can get directly these thermodynamic properties. We started this chapter with reviewing some basic laws of calculus, and then we explained the fundamental laws of fundamental property relations of thermodynamics. We said we have four fundamental property relations. We have Maxwell relations. We have some relations for thermodynamic properties, such as thermal coefficient compressibility, isothermal expansion, heat capacity. And we used all of these laws and relations in order to see how we can derive mathematical models for thermodynamic processes, and how we can use like equation of a state in order to find some of these partial derivatives. Today we will talk about the residual properties, one of the methods also we can use in the thermodynamic models to find these like the values of the thermodynamic properties. Okay, so to explain the residual properties, we will start with an example and then see what are the challenges we have in this example that makes us use the residual property. What are the new things in this example that we can't use or solve it similar to the previous examples we did in the previous lecture. So this example says we have methane. This methane enters a turbine at 600 Kelvin, 1 megapascal, and leaves at 400 Kelvin and 0.2 megapascal. So we have the inlet pressure and temperature, outlet pressure and temperature also given. How much work is produced for each mole of this gas? So we need to find what is the amount of work needed per each mole of the gas. And he said use van der Waals equation of a state. We have the value of parameter A, of van der Waals equation of a state, value of parameter B, and if you need to use the heat capacity, use appendix D to get the value of the heat capacity. Okay. So this is the example. So basically this example needs to calculate what is the amount of work per unit mole. One of the things that I observed in grading the exam, that if you have turbine, for example, or if you have compressor, so some of you get confused the type of work we have in this one. So again, if you recall chapter 1, we have three types of work. Like we have work of expansion, contraction, we have flow work, we have shaft work. So each one is related to like certain function of the process. So if you have pipe and you have inlet and outlet of this pipe, then you can have like flow work, for example. Here in this example, we have turbine. So one of the characteristics of the turbine that we have rotating equipment, or rotating like motor or mixer. So this means we have shaft work. And again, compression and expansion. If you have piston, this is an example of work of expansion, contraction. Okay, so it's very important that to know what is the type of work that you need to find, like in any of the examples, to understand the process, to know what type of the work that you need to find, or what type of the work that is given in the problem itself. So here in this example, we have turbine. So we know that in turbine we have rotating like machinery. So this means we need to find the shaft work. So this is why here directly he put the shaft work, simple of the shaft work. Okay. So in order to solve this problem and to find it, the shaft work, this is something we can find from the first law of thermodynamics. So this is chapter 4. So we can recall the first law of thermodynamics. So this means we have the accumulation term equal inputs minus outputs plus work plus Q. This is the general form of the first law of thermodynamics. Okay. In this example, we have open system because we have inlet, we have outlet. So since we have open system, then we can say this equation will be accumulation equal mass flow rate of the inlet times specific enthalpy plus V square over 2 plus GH, and all of this for the inlet, minus mass flow rate of the outlet times specific enthalpy plus V square over 2 plus GH, and all of this for the outlet, plus shaft work plus Q. We don't have work of expansion contraction in this one, and the flow work is already embedded in the enthalpy that we have in the inlet and outlets. Okay, let's put it work of expansion contraction, put all the terms here. Okay. So if we recall from previous chapters, we can make some assumptions to simplify this example. So we can assume, so in the example, he doesn't mention we have any changes, we don't have any changes with time. So we can assume the process is steady state. So this means the accumulation term will be cancelled because we have a steady state process. There's no difference in the elevation between inlet and outlet. Okay, so here one, there is no elevation change. Between inlet and outlet. So this means the term of the potential energy for the inlet will be cancelled with the potential energy for the outlet. And again, we don't have any like changes in the pipe diameter, the diameter of the inlet, the diameter of the outlet. He didn't mention that we have any changes in this one. So we don't have no changes in inlet and outlet diameter. So this one means the kinetic energy of the inlet, the kinetic energy of the outlet, both of them will equal, so we can cancel both of them together. We have this process can be assumed to be adiabatic. And adiabatic means we don't have any heat transfer between the system and surrounding. And we don't have piston. So this means we don't have any expansion or contraction happening due to piston movement. So as a result of these like assumptions and based on the equation we have, and again one more thing to, let's put it this way. So we can say this energy or the first law of thermodynamics will be 0 m dot of the inlet times specific enthalpy of the inlet minus mass flow rate of the outlet times specific enthalpy of the outlet plus shaft work. So this will be the final form of the energy balance equation we have. If we recall that in the example, it's given, or in the example it's required to calculate the shaft work per number of moles. Here in this example we don't have number of moles, we have mass. This is why we are using specific enthalpy. So we can adjust the equation to be consistent with the requirement that we have here. So we see the same equation can be written in this way as molar basis. So 0 will be molar flow rate of the inlet times molar enthalpy of the inlet minus molar flow rate of the outlet times molar enthalpy of the outlet plus shaft work. So we can play with the bases. We can have it in as a mass basis or we can have it as mole basis. So in this one we'll have molar. So this one here we have molar. And in mass basis, if you have mass, then we have a specific. If you have mass, then we have a specific properties. Okay, so we can rewrite the equation when we can say then we have and one more thing before like putting the equation in this way. And here in this example we said we have accumulation, and if you remember from the conservation of mass, so principle of conservation of mass said if you have like accumulation equals 0, steady state process, so the inlet and outlet will be the same. So the inlet moles equal the outlet moles, and this will be equal to n dot. So all the moles inlet and all the moles outlet will be the same. So then we can rewrite the equation we have and say then the shaft work divided by number of mole, this will be molar enthalpy of the outlets minus molar enthalpy of the inlet, which is the change we have in the molar enthalpy in the system. And this is the property that we need to calculate. This is what we need to calculate. So in order to find this one, just we need to find delta H. So what is the enthalpy change? Substitute in the energy balance equation, then you find the shaft work that we have in this problem. Okay, so now this is what we need to start like trying to find. That's DH. So far is clear? Any questions? Okay. So now let's find DH, the enthalpy change for this process. So here in this one, we start with using the total derivative. So if you remember the general form of the total derivative, it says dx equal dx by dy at constant z dy plus dx by dz at constant y dz. This is the general form of the total derivative. We start then to put the symbols we have. dx, as we said, this is the variable that we need to find. So this will be enthalpy. Then we have y and z. Y and z can be any like two variables we can select. And if we return to the example, so the example here we will see that we have like temperature and pressure of the inlet, temperature and pressure of the outlet. So we have complete information for temperature and pressure. So we can select them as z and y. So we can say we can select y to be temperature. We can select z, this one, to be pressure. And if we did this, so this will be the equation we have. dH, this will be dH by dt at constant pressure dt plus dH by dP at constant temperature dP. So now we have like two partial derivatives. Again, number one, see the fundamental property relations. Can we replace any of these partial derivatives with a direct thermodynamic property? And the answer is yes, because we have this one here, and we can replace this one with heat capacity at constant pressure. Okay, so one of them is gone. Now for this one, if you look this one in the fundamental property relation, you will not see like this partial derivative exist. If you look for the Maxwell derivative, so again, this one will not exist. So we need to use the basic calculus rules in order to find this one. And in terms of these rules, we have two things. We have the triple product, we have the expansion rules. Any one of them that you can use. This one we can use as the expansion rule. an expansion rule that we will see dH by dP at constant temperature. Expansion rules, we will have 4 brackets. So this is 1, 2, plus 3, 4. And I start putting the variables. Here we will add dH. Here we will add dH. Then here we have dP at constant temperature. And here we will have dP at constant temperature. Then we need to define 2 new properties we have here. Any 2 new properties. Can select temperature, pressure, entropy, internal energy, enthalpy, any new properties that you can define. So what are the properties I will define? So the properties that you will put to make you directly replace the partial derivatives with direct thermodynamic property or replace it with another partial derivative from Maxwell relations. So based on this concept, we can say we can select entropy and pressure. So this one if can be entropy. And here I can put pressure. So if I did this one, now I can see the following. Here I have dP by dP. This is 1. Derivative of variable with respect to itself. This one here, from fundamental property relations, is molar volume. Okay. This one here, from fundamental property relations, is temperature. And this one, from Maxwell relations, will be negative dV by dt at constant pressure, and this is partial derivative we like to have. VTP, 3 variables, then we can use equation of state to solve this one. So again, dH by dP at constant temperature, I use the expansion rule. So now in the expansion rule, I replaced all the partial derivatives, either with values, similar to 1 for example, or thermodynamic property, temperature and molar volume, or even I replaced the partial derivative with another partial derivative that I can solve using equation of state. Okay, let's put all the equations right now together. So now we can substitute in dH equation, and then we can say dH equal Cp dt plus V minus T dV by dt at constant pressure, and all of this times dP. So this is the whole formula we have right now. If you can substitute in this formula, find the enthalpy change, then we can substitute in the first law of thermodynamics, find the shaft work. Okay. So here in this example, we have 2 things. We have 2 things to observe. The first one is this one, a new partial derivative here, and this one easily we can obtain from van der Waals equation of state. So we don't have any problem to solve this one. We have problem with this one. Cp, which is heat capacity, in the example he said we will use appendix D to find this thermodynamic property. Okay. And one of the things that we have in this problem, that the value of Cp, let's put it this way. So if we need to comment on this one, so value of Cp, if we have case number 1, if Cp is constant, similar to the examples, the first example we solved in the previous lecture, then we can substitute Cp value, then make the integration, solve the problem, and we are done. Okay, so let's say if, for example, Cp is 5/2R then put it, made the integration, remove this partial derivative, substituted with van der Waals equation of a state, and we solve this problem. This is the first example. And this is the combination of the first and second example we solved in the previous lecture. We have another scenario. If Cp is not constant and in the problem we have low pressure value, then Cp will be function of temperature. And then we can go to the appendix D, pull the equation of Cp, put it here, and make the integration. And we solved this in chapter 3. The long equation of Cp we got from from appendix D, and we have A, T2 minus T1 plus P over 2, T2 square minus T1 square plus C over 3, T2 cube minus T1 cube, and so on. And the third scenario in this problem, if Cp is not constant and you have high pressure. So in this case, Cp will be function of temperature and pressure. And this is the case we have in this problem. So again, so far this example is similar to what we solved in the previous lecture. Okay, and we can continue solving the same way we did in the previous lecture if we have Cp is constant. Or if we have Cp is constant, is not constant, and the problem itself at low pressure value. Because even if at case 2, Cp is function of temperature, so we can the formula of Cp, make the integration very easily and solve it. But if we get back to this problem, so this problem here, we have the pressure is 1 megapascal. We have the pressure 0.2 megapascal, and this is high pressure value. At high pressure value, the heat capacity is function of pressure and temperature. And this is the problem here. Here, Cp, we are like integrating it with respect to the temperature. So this equation, delta H equation we have right now, it accounts for the heat capacity change only with temperature, not with pressure. So we need to make some changes to make sure that we are like seeing how this heat capacity will change with pressure and with temperature, like both of them. Before we continue solving this one and explaining the need of the residual property, let's see this table. So this table gives you an idea of Cp values, how the Cp values are changing at low pressures and at high pressures. So at 350 Celsius, for example, Cp is 2 at 0.01 megapascal. At 0.05 megapascal, still it's 2. At 550 degrees Celsius, so heat capacity 2.16, 2.16. Even if the pressure is like 5 times, but the value of the pressure is low. 750 degrees Celsius, extremely high pressure. We still have 0.01 megapascal, 0.05 megapascal, and the Cp is constant. This is why we said if you have low pressure value, the value of Cp is function of only temperature. So if you can compare the numbers, you can end up with this one. You have very small difference between Cp values at different pressures. So only Cp is affected by temperature if we have low pressure. So this is why if you have low pressure, assume Cp is function only on temperature, pull the equation from appendix D, pull the integration, and that's it. But if we go to the high pressure values, 1 megapascal, 5 megapascal, and let's get the first temperature, 350. So at 1 megapascal, Cp is 2.12. At 5 megapascal, 2.7. So now we'll have difference. So the pressure is affecting the value of Cp. And if you go to the temperature, compare Cp at 350, compare Cp at this one, so we still have changes in the Cp with pressure and with temperature. So we have large difference happening. So this is why at high pressure, we are saying pressure and temperature, both of them affecting the heat capacity. So far it's clear? And this is the 3 notes we said. If you have ideal gas or real gas at low pressure, heat capacity, enthalpy, only function of temperature. Real gases at high pressures, then we have heat capacity and enthalpy depend on temperature and pressure. Okay. So now we can solve the enthalpy. We cannot integrate the previous equation directly because this previous equation says Cp will be integrated with respect to temperature. and neglect the pressure effect on the CP. So we have something missing in this one. And this is why here we have a definition of something called the residual property. Residual property, this is the key that we can use to complete your thermodynamic derivation if you have high pressure problem and you have heat capacity in the equation that you have. So in general, residual property, we are using it in case we have heat capacity in the equation and this problem itself at high pressure, okay? Because the model we have so far doesn't account for pressure and temperature changes. So we need to add this in the thermodynamic model. Residual property in general, this is the difference between an intensive property of the real compound and the intensive property, same intensive property for this compound in case if this compound is ideal at the same temperature and pressure. And this is the mathematical formula of it. So residual property of any property or a residual property of like any intensive property is the value of the intensive property at real or for real gas minus the value of the same intensive property if this gas is ideal gas, okay? And intensive properties, again, specific or molar enthalpy, specific or molar internal energy, specific or molar entropy, okay? So this is the definition of residual property. And if you will use the residual property, then we will have another like concepts we need to remind you, and this is explained, I think, in chapter 3, that if you have like process, and this process we have changes happening from this state to this state, and I ask you to calculate the enthalpy change or entropy change or internal energy change. So you can find like the enthalpy at this point, enthalpy at this point, subtract both of them, then you can see the enthalpy change. Or you can assume I will move from this point to this point, not on the black line, I will move on these two processes. So if you find the enthalpy change for this step, enthalpy change for this step, sum both of them together, you will find the enthalpy change for the original path. Or you can assume I will go this way, I will go this direction, then I will go this direction, then I will go here till the end. So I have 3 steps, step number 1, step number 2, step number 3. Calculate the enthalpy change for step 1, enthalpy change for step 2, enthalpy change for step 3, sum all of them together, so this will be the enthalpy change for the original path you have. Okay, so here we have an idea of hypothetical paths. So if you have a path, then you can assume if I didn't take this original path, I will go from a different path, okay, you will have the same like property change because you have intensive property. You remember, this is why we said we prefer to work with intensive properties, not extensive ones. Also, we prefer to work with state functions, not path functions, okay? So this is a state function. So if you have any way you have here, just see the paths you have, and then you can find the change you have in the properties. Residual properties can be calculated, as we said, for internal energy, enthalpy, entropy, and we have many equations we can use. In the textbook, there is derivation for this one. So if you're interested to see where this equation comes from, so you can check the textbook. You have the full like derivation for this one. But in the textbook, we have equations. We can use any of these equations to calculate residual property of entropy, residual property of enthalpy, residual property of internal energy, and all of these properties with respect to pressure change. Or you can have the same residual properties calculate internal energy, enthalpy, entropy, residual, and all of them with respect to molar volume. So you can have both of them, and you can use any one of them in the problems. Okay? So now let's see how we can apply all of this idea again in our example. So in our example, we have this inlet condition, 600 Kelvin, 1 megapascal. We have the outlet, 0.2 megapascal, 400 Kelvin. So we will assume that the working fluid will not go directly from this inlet condition to this outlet condition. Okay, so what will happen? We will assume that this is the initial case. And at this one, the working fluid conditions will change to pressure equals 0 and to temperature 600 Kelvin. This will be path number 1. Okay, so the pressure and temperature will not change together at the same time. First step, the pressure will change from 1 megapascal to 0. Why I select 0? Because this is vacuum condition. At this condition, I can assume I have ideal gas behavior. Okay, so this is why I select this pressure value. Now I will have the temperature will change at constant pressure. So now temperature will change to 400 Kelvin. And this will be path number 2. Then the pressure will change to 0.2 megapascal at same temperature. So this is the hypothetical path. I will assume that the temperature and pressure will not change directly together at the same time from the inlet and outlet temperature, but instead I have 3 steps happening. The first step, pressure will change at constant temperature and pressure will change to 0 pressure, because at this pressure I can assume ideal gas conditions. Then pressure is constant and temperature will change from initial or inlet to final conditions. Then this is the final temperature, so it will be the same, and pressure will change from 0 to 0.2 megapascal. So now if you need to find the enthalpy change for this original path, let's call it delta H star. So what you need to find delta H for path number 1, find the delta H for path number 2, find delta H for path number 3, and then you can say delta H star for the original path, and this is what is equivalent to shaft work divided by number of moles. This is what we need to calculate. Okay, this is equivalent to molar enthalpy change for path number 1 plus molar enthalpy change for path number 2 plus molar enthalpy change for path number 3. Clear? Any questions so far? Okay. Path number 1 and path number 2. Path number 3, here we have this condition, we have this condition. This condition at the same temperature, right? But here we have high pressure, here we have low pressure. At this low pressure, we can assume we have ideal gas. Make sense? So here this is enthalpy for real gas, this is enthalpy for ideal gas, and this is the definition of residual property. The property of real gas minus the property at ideal gas conditions. So path number 1, this is the residual property. Path number 3, again, real condition and ideal condition. So path number 3, this is also residual property. Path number 2, we have changes happening at constant pressure, and this pressure is very low. So delta H2 can be assumed by ideal gas, and we can say delta H2 for ideal gas is Cp dt, and that's it. So now the original path, the delta H star I need to find, I divide it into 3 parts. The first part, or the first path, this is real condition, this is ideal gas condition. Difference between real and ideal gas condition, this is residual property. So path number 1 is residual property. Path number 3, real condition, ideal gas condition. Difference between real and ideal is residual property. So path number 3 is also residual property. Path number 2, we have low pressure, pressure equal to 0. So we have ideal gas. So here we have temperature change at very low pressure, temperature change while the gas is ideal. So at this condition, we can assume ideal gas, calculate the enthalpy change for the second pass with ideal gas, which is just very simply Cp dt, and that's it. Because at this low pressure, Cp is only function of temperature. Make sense? So again, so this is the conditions we have. First pass, isothermal, pressure change, delta H of this pass is ideal minus real. So this one is minus H residual. Here, real minus ideal, so this is H residual. Here we have temperature change for ideal gas, so delta H is H2 ideal gas minus H1 ideal gas, which is Cp dt. And this is now we need to find. We need to find like delta H1, delta H2, delta H3 in this problem, and that's it. So now if we start solving this one, let's start with the easiest one. Path number 2. So we have dH2 is Cp dt So by integration, then we will have delta H2 is the integration from T1 to T2 Cp dt. And again, Cp is not constant. We need to find Cp from appendix D. And from appendix D, let me put the equation. We have Cp over R. This is equivalent to A plus Bt plus Ct square till the end of the equation. The value of C, this one is 3.631 times 10 to the power 5. The value of B, also we'll find from the appendix, is negative 8.975 times 10 to the power negative 3. The value of A, also from the appendix, this will be 4.568. And the ideal gas constants, just to be consistent with the SI system, this we will select 8.314 joule per mole Kelvin. So we will integrate this equation. So if you remember this one, delta H2, this will be AR T2 minus T1 plus BR over 2 T2 square minus T1 square plus CR over 3 T cube minus T1 cube, etc. till the end of the equation. So we know the value of A, we know value of B, value of C, R is given, T1 and T2 given in the problem. So we can substitute in this one and we will find delta H2. This one is negative 9289 joule per mole, and this is, let's call it equation A. So this is the first path that we have here. For the second path, or let's start with the first path. Okay, so we have given HR equation. We have residual property HR. This is RT Z minus 1 plus integration from infinity to molar volume T dP by dt at constant volume minus P, and all of this dV. So this is the residual property. This equation will be given. Also we have van der Waals equation of states. And van der Waals equation of states says pressure is RT over V minus B minus A over V square. So we will use equation of states to find this term. So this term will be obtained from the equation of states, and from this one we will see dP by dV sorry, by dt. So this one will be R over V minus V. Just we will integrate this pressure equation with respect to temperature. So substitute in HR equation. So now substitute here in residual molar enthalpy. Then we will see that residual molar enthalpy will be RT Z minus 1 plus integration from infinity to molar volume RT over V minus B, and this comes from here. Then minus P, and this one will come from the van der Waals equation of a state. So this one RT V minus P plus A over V square and all of this dV. And we will see that this term will be cancelled with this one, and the remaining of this equation will be RT Z minus 1 plus integration from infinity to molar volume of A over V square dV. And if you make this integration, this will be RT Z minus 1 minus A over V. So this is the equation we have for the residual property. And this is the equation that we will use This is the equation we have, the final equation we have for the residual property. And this is the equation we will use to substitute for path number 1, path number 3 to find both of them. Okay, so if we did this for the first path, so for path number 1, so for this path we have like P1 1 megapascal, we have temperature 600 Kelvin, and they will change to 0 megapascal, 600 Kelvin. This is the first path that we have. We need to substitute in this equation. So substitute with this condition. Substitute in van der Waals equation in order to find the molar volume, and the molar volume will be 4.986 times 10 to the power negative 3 meter cube per mole. And for this value, substitute in Z equation compressibility factor. So we have Z is P V over RT. We have pressure, we have volume, we have temperature. Substitute here with this term, and we will see this one is 9995. And now we have HR equation, residual equation, which is RT Z minus 1 minus A over V for the first path. We have the value of R, we have the value of temperature, 600 Kelvin, we have the value of Z, we just calculated, we have A is given, we have molar volume, we just calculated, so we can substitute here, and we can see the residual for the first path. This is negative 47.8 joule per mole. And we call this equation B. Then we will go to the third path. So for the third pass, we have 0 megapascal, 400 degrees Celsius, and this should change to 0.2 megapascal and 400 degrees Celsius. So the same thing, we will use the real conditions, substitute in van der Waals equation of states to find the molar volume, which will be 0.01659 meter cube per mole. Use this value to calculate the compressibility factor, which is PV over RT. So this pressure, 0.2 megapascal, 400 Celsius, this molar volume value, and Z will be 0.998. So now we can get back to residual property equation, which is RT Z minus 1 minus A over V. Substitute with the conditions we have here, then residual property for path 3, this will be negative 20.5 joule per mole. And this is equation C. So now we know that delta H star, which is delta H1, first path, plus enthalpy change for second path, plus enthalpy change for third path. So this is equal to negative H1 residual plus delta H2 plus H3 residual. So from A, B, and C, put all the numbers here, then we will see this delta H star, which is equivalent to shaft work divided by the number of moles. This one will be negative 9261 joule per mole, and this is what I need to calculate at the end. Is it clear? So let's recap what we did in this example. So in this example, this is similar to the previous examples we said. We have thermodynamic models. We need to find the change happening in one of the thermodynamic properties. The issue we have in this example that we have Cp is not constant and we have the pressure is high. Again, if Cp is constant, the example will be easy. If Cp is not constant and we have low pressure, still the example will be easy because Cp will be a function of temperature. But if Cp is not constant and the example at high pressure, so then here we have an issue with this one. Because at high pressure, the value of heat capacity, function of pressure and temperature, and the thermodynamic model we have capture only the temperature effect on heat capacity. So how can we quantify to the pressure effect? At the same time, we need to make hypothetical path. So we will assume that the substance of the working fluid is not changing directly from the inlet to the final conditions, but we have like intermediate paths that happening. So pressure will change to the ideal gas conditions, to vacuum. Then we have temperature will change at constant pressure, and then we have pressure will change again to the final condition. Then we will start to analyze each path. The path that we have temperature change at zero pressure, this is ideal gas condition. So you can assume delta H, for example, is CPdT. Delta U is CVdT. And at this condition, very low pressure, pressure is zero or vacuum, so pressure has no effect on Cp value. So you can integrate directly the equation you have in the appendix. The other paths that you will have pressure is changing from high pressure to vacuum, this can be calculated by the equations for residual properties. Because you need to find the property at real condition minus property at ideal condition. And always remember, the property at real minus property at ideal condition, this is the residual property. And we have equations directly for residual property we can use. So we will use the residual property at these two paths, but then the residual property may contain partial derivatives, but these partial derivatives containing PVT. So we can contain the value of this partial derivative from the equations we've stated directly. So we can put all of them together, analyze the residual property equation to be in a simplified form we can substitute in use this simplified final form of the residual property equation, one time at the conditions of the first path, one time at the conditions of the third path, and then you have 3 enthalpy changes or 3 property changes. Sum all of them together, and this will be the total property change that you need to calculate. Clear?